This section of the book is on linear approximation, and there's also differential approximation and Newton's method, but all three of those are a type of linear approximation. Linear approximation is almost a funny application of derivatives, because when we started derivatives back at the beginning of the book, we understood what the average rate of change meant, and we used our intuitive knowledge of the average rate of change to get better and better approximations to this thing that we wanted to call the instantaneous rate of change. So we knew average rates of change, and we used those to get our notion of instantaneous rates of change. Now that we have so many formulas for calculating derivatives quickly and easily, we do things kind of in reverse. We know how to calculate derivatives, and now we use the derivatives to approximate the average rates of change, at least if your change in x is small. And this topic is called linear approximation. To be honest, it's not as important as it used to be. Again, calculators and computers have made exact calculation, or calculation to all the decimal places that you want, very, very easy, or all the, out to 11 decimal places, or some systems will go out, you name how far you want them to go out, they'll go out that far. It's still true that linear approximation and differential approximation are important in formulas, so that you use this approximation once, write down a general formula, and then you can apply it in lots of different situations, something that you can't do by calculating one example one time, more or less exactly on a calculator. So it's still valuable, just not as valuable, but still very useful. So how does linear approximation go? Well, what's the derivative? I'm going to say the derivative of a function at some x coordinate a. Well, we frequently take the limit as h approaches 0, but now I'm going to say the limit as x approaches a of f of x minus f of a over x minus a. This is another way of writing the limit that defines the derivative. Frequently we name x minus a h, and then this would be the limit as h approaches 0, and this would be a plus h. But this will be nicer for us right now in this application. So when x, what does this mean? So it means the limit as x approaches a. So you should think, oh, I can make this arbitrarily close to this thing called f prime of a by making x close enough to a. Fine. So what we think is, okay, well that means f prime of a should be approximately equal to f of x minus f of a over x minus a if x is close to a. Now, of course, this doesn't mean anything rigorously mathematical, that this should be approximately this if x is close to a. It's part of the point of limit that it makes precise what you mean by close enough and how good you want this approximation to be. Yeah, you take the limit and it's an equality. But we do have kind of an intuitive notion in various circumstances of what approximately equal to means and what close to a means. So yes, they're kind of vague terms. And how good's the approximation? Well, if you could say exactly how good the approximation was, then it wouldn't be an approximation because you'd know exactly what the value was. But anyway, so we do write this, even though you could argue that, well, but that doesn't mean anything. Well, we'll see, do some examples. But so if you multiply both sides by x minus a, you get that f prime of a times x minus a should be approximately f of x minus f of a. And now if you add f of a to both sides, you get f of a plus f prime of a times x minus a should be approximately equal to f of x. So this is some very simple function of x. If you fix an a, then f of a is just some constant. F prime of a is some constant. At a is a constant. This is just some linear function, some constant times x minus a constant plus a constant. This is just some linear function, and we give that, so something of the form y equals mx plus b. We give that a name. You can write lots of complicated things like this. So you indicate the function that you started with, and you indicate your fixed value of a, and you write all this notation. But if f is clear and a is clear, we would frequently just write this as L of x. This is the linearization of f at a. This simple function, and the whole point is that at least for x close to a, so that's the linearization, the linear approximation is just that this linearization should be approximately f of x if x is close to a. It's also called the tangent line approximation. Why would it be called the tangent line approximation? Well, what is the graph of the linearization? So here's some function. We start with a function f of x, and you pick a point a, some x coordinate a that you're interested in, and you calculate the linearization. So here's the linearization. It's f of a plus f prime of a times x minus a. The graph of this. So you graph the function y equals f of a plus f prime of a times x minus a. What is this graph? Well, for a fixed a, this is a constant, this is a constant, that's a constant. The graph of this is a line, so the graph of this, the graph of the linearization is a line. What line? Well, it's slope. You could write this in slope-intercept form. If you multiply this out, you get f prime of a times x. And then the constant terms, there'd be the f of a, and then a minus a times f prime of a. So the slope is f prime of a, is a line with slope f prime of a, and it clearly contains the point when x is a, y is f of a, containing the point. So it's a line that contains a slope f prime of a, and it containing the point a f of a. Well, that's exactly what the tangent line was. The tangent line at the point a f of a on the graph of f, so this is on the graph of f, so here's a point on the graph of f, and we take the line that contains that point with slope f prime of a. That was the definition of the tangent line to the graph of f at x equals a. So this is the tangent line. To the graph of f at a. So yeah, the tangent line approximation, linear approximation. Graphically, what you're doing when you use the linear approximation is you're approximating a function by, if you draw the graph, you'd be approximating the function by its tangent line. So it's, if you were to use a parabola, so like y equals x squared, and you approximate here using linear approximation or the tangent line approximation, then what you're doing is instead of you pick at various x coordinates, instead of getting the corresponding y coordinate on the parabola, you'd be getting the corresponding y coordinate on the tangent line. And when you're close to this point, that should be very close to the graph. All right, so that's linear approximation. Let's do an example. It is possible to give some kind of bounds on how bad the approximation can be in terms of second derivatives or other information. I'm not going to discuss that. It is in the book. It's fairly technical. It's, I don't know, it's a lot more difficult than actually applying linear approximation to figure out the worst possible approximation you're getting to do it. But let's just do the approximations without worrying. Well, we'll use a calculator to kind of see how good our approximation is. So let's use linear approximation to approximate the natural log of x at x equals 1. So example, let's let f of x equals the natural log of x and find the linear approximation at 1. Or find the linearization of f at 1. And use it to approximate the value of the natural log of 0.9. All right. Okay, so the linearization of f of x, it's f at 1 plus f prime at 1, so at 1, times x minus 1. This is what we need to figure out. Okay, so this is L of x, f of 1, the natural log of 1, plus f prime at 1, so we need f prime of x is 1 over x. So f prime at 1, 1 over 1, wait, I'll do it in my head, 1. So we get 1 times x minus 1. The natural log of 1, you should know that without a calculator, that's 0. So this is x minus 1. So what we're getting for the linear approximation, L of x is x minus, for the linearization, we're getting L of x is x minus 1. The linear approximation then is telling us that ln of x is approximately x minus 1 if x is close to 1. Okay, so that's what you get for the linearization and the linear approximation at any x coordinate close to 1. 0.9 is relatively close to 1. Of course, it depends on your problem, whether that's close enough for whatever application you have in mind. But let's see what approximation we get. So the natural log at 0.9, well, that should be approximately x minus 1, where x is 0.9. So 0.9 minus 1, so negative 0.1. That's what we get, that the natural log of, so linear approximation gives us that the natural log of 0.9 is approximately negative 0.1. What does a calculator give you? Let's see, I did this. My calculator gave me, to all the decimal places in its display, that the natural log of 0.9 is approximately minus 0.10536051566. Okay, right. Calculator gave us this. This is pretty good. I mean, we're getting, the next decimal place is a 0. Our approximation is pretty good. But I'll say it again. The value of linear approximation, even in this age of calculators and computers, is suppose we don't want this just at the fixed, we don't just want to approximate 0.9. We've got some formula, some problem where we're only concerned with values of some physical measurement that are close to 1. Then it might be very important to be able to simplify that formula formula using that ln of x is approximately x minus 1, whereas your calculator can tell you what you get for each fixed x value. It's not going to tell you this. All right, let's do another example. Let's do f of x equals 1 plus x to the p. So let's approximate. All right. Let's find the linearization of f of x equals 1 plus x to the p at 0. And use it to approximate. So, and approximate, we'll use it to approximate the square root of 0.99. Okay? So, what do? Use linear approximation, or you write down the linearization. So, you write L of x is f at the specific x value where you're calculating the linearization. So it's 0. So we get f at 0 plus f prime at 0 times x minus 0. Okay, f of 0, 1 plus 0 to the p, 1 to the anything, it's 1. So we get L of x is 1 plus, we need f prime evaluated at 0. So I think I'll fit that right here. F prime of x is, use the power rule, bring the p down, you subtract 1 from the exponent. And then by the chain rule, you have to multiply times the derivative of the stuff inside, but that's just a 1. So we get this. So what's f prime at 0? F prime at 0, you would get 1 to the p minus 1, that's 1, but times p. So we get p. So f prime at 0 is just p. And so this is p, and this is x. So the linearization of 1 plus x quantity to the p is L of x equals 1 plus p to the x. And linear approximation then says 1 plus x to the p is approximately equal to 1 plus p times x if x is close to where we calculated the linearization, if x is close to 0. All right, so that's what linear approximation is telling us. We would like to use this to approximate the square root of 0.99. How do you do that? So we just found that 1 plus x to the p is approximately 1 plus p times x if x is close to 0. And we want to approximate the square root of 0.99. How do you do that? Well, somehow you have to make this look like that. Well, the square root is the 1/2 power. So we need to write this as 1 plus something to the 1/2 power. We want 0.99, so the something needs to be negative 0.01, right? And so we get that this is approximately equal to 1 plus p, which is 1/2, times negative 0.1. So what is this? Well, this is 1 plus negative 0.005. So that's 1 minus that. This is 0.995. So that's what linear approximation gives us. Linear approximation tells us that the square root of 0.99 is approximately 0.995. What does a calculator give us? according to my calculator, which is still an approximation. It's just accurate to a lot of places. According to my calculator, and in fact, I hope I didn't write equals a minute ago, because when I did the calculator calculation, because that was an approximation too. This is approximately 0.99498743711. But the point is that this is extremely close to 0.995. Yeah, there's a 4 there, but then there's a 9 right there and an 8. I mean, this is very, very close to 0.995. So linear approximation, it's pretty good, especially considering how little work it is. All right. All linear approximation problems are basically like these two examples that we did. But there's another way of writing linear approximation and another type of question that's asked when you write linear approximation in this different way. That approximation is called, or that different way of expressing the linear approximation is called differential approximation. It's, the notation is both obvious and confusing at the same time. Probably wouldn't be confusing if we didn't emphasize that it looks like it says something it's not really saying. So let's look at differential approximation. This is no different from linear approximation, except you write it differently, and typically problems where you would use it in this form are phrased in a different way than linear approximation problems. So what do? You've got, we had that f prime of a is approximately equal to f of x minus f of a over x minus a if x is close to a. Okay. What is this? And this is how we got linear approximation. But if you just say that f prime of a is approximately equal, and think of this as, well, it's the change in f, and if y equals f of x, then we would think of this as the change in y over the change in x. And so, and in fact, we don't need to call this a now. I mean, we had to have a here to distinguish between x and a, but you could say f prime of x is approximately the change in y over the change in x if the change in x, so if x is close to a, that's if delta x is close to 0. All right, and that means that delta y, if you multiply both sides by delta x, is approximately f prime of x times delta x. Or, in more suggestive notation, use the Leibniz notation. The change delta y is approximately dy dx over delta, or times delta x, if delta x is close to 0. Okay. Well, fine. So this is linear approximation, but in a form that cares more about the change in x and the change in y instead of the actual value of x and the value of y. But that's the only difference, except how we write it. And the way we write this is, all right, so we have this. This makes sense. Delta x is some number, and dy dx is some number, And you multiply those together and you get the approximate corresponding change in y. Fine, fine. But this is so suggestive that, oh, it's like if this had only been a dx, it would cancel with that dx, cancel, even though this isn't a fraction, still it would look like that's what's happening. And you'd get a dy. And that notation is so suggestive. That is the kind of thing we write. And then you have to ask yourself, what does it mean? So we do write this. This is called, these separate dy and dx's are called differentials. What do they mean? Actually, you're supposed to think of them as this is an infinitesimal change in x, and when you multiply this quotient of infinitesimals times it, the dx's cancel and you get dy. It's possible to make that rigorous in a course called in a calculus course that uses something called non-standard analysis. But for us to make it rigorous, all we say is this dx, this dy dx just denotes the derivative. That's no problem for us. That dx right there by itself is just a single variable name. It's not necessarily related to x. It can be anything. It's just some variable. We could call it banana or u or something and call this one v. dy is also a variable. And all we're saying is I'm calling dy what I get when I multiply dy dx by this other variable. But the reason we write it this way is because, so we do write this, that dx can just be anything, and dy dx is the derivative, and dy is what you get after you multiply dy dx by whatever this is. But the whole point is, of the differential approximation, is that delta y then is approximately this dy if dx is close to 0. Because that's what this says. So we can let dx be anything here, but we care about it being a small change in x. So we think about it as being delta x. So, and if delta x is small, so if dx is small, then linear approximation is the same as saying the corresponding delta y is small. But we're calling this product dy. And so, it's the same as saying that linear approximation is the same as saying dy dx times this small change in delta x gives you the corresponding small change in y. And we're calling dy dx times any variable, we're calling that dy. So what we get out of that is this differential approximation, that the change in y is approximately dy, which is this quantity that you get by taking dy dx times dx, if dx is close to 0. All right, let's do an example so that you can see what's different about what you write when you're using differential notation. We will come back to differential notation when we look at antiderivatives. It'll be very important to us that we write this kind of thing and that it has meaning. It just doesn't exactly mean the cancellation of the dx terms. All right, so here's an example. Suppose a spherical container has a radius of 1 meter. So we've got this spherical container. It has a radius of 1 meter, but whenever people make physical measurements, they're aware of the fact that because of their measuring equipment or just the whole physical situation, that there could be some error in their measurement. And what you frequently see in actual physical problems involving measurements is this has a radius of 1 meter to within plus or minus 0.001 meters. So that doesn't mean that its radius is either 1 meter plus this or 1 meter minus that. It means that it's anywhere between 1 meter minus 1 millimeter and 1 meter plus 1 millimeter. It doesn't have to be exactly one of those. It's somewhere in between. So this is the way people write measurements. They mean that, yeah, I measured it as being this, but I'm only sure of my measurement to within plus or minus 0.001 meters. So maybe I'll write to within here. All right. The question is to approximate the error, the corresponding error, possible error in the calculated volume of the container. Okay, that's our problem. How do you do that? Well, we have to know some relationship between the volume of the container and the radius of the container. But we're told it's a sphere, so you're supposed to know the volume of a sphere. Volume of a sphere, so the V, the volume, is 4/3 pi r cubed. Okay, r is the radius. I'm going to call this r. In meters. Approximate the corresponding possible in the calculated volume. This is V in cubic meters. The volume is this. And if we knew that the radius was exactly 1 meter, so if r is 1 meter, then V is would be exactly 4/3 pi times 1 cubed, would be exactly 4/3 pi cubic meters. But we don't know that r is exactly 1 meter. And we'd like to say, so we don't know the volume is exactly this. We'd like to say the volume is approximately this to within plus or minus something. Now we're actually getting an approximation on the error. So this isn't even the exact error. So, but still, this is actually used in a lot of engineering and physics applications, this differential approximation of error. So what are we interested in? We're actually interested in delta V, which would be approximately dV. Right? We'd like to know that if we change r, the radius, by plus or minus, or somewhere within the range of plus or minus 0.001 meters, that could change V by a certain amount, and we want to approximate that change in V. So we're going to approximate that with dV. But what's dV? Well, differential approximation. dV, in differential notation, dV is dV dr times dr. Yes, it looks like the dr's are canceling. So, but we have V as 4/3 pi r cubed. 4/3 pi is a constant. The derivative of r cubed with respect to r, 3r squared, the 3's cancel. So we get 4 pi r squared times dr. So in differential notation, dV equals 4 pi r squared dr. Yes, it's exactly the same as saying that dV dr is 4 pi r squared. So yes, it looks like you multiplied, it looks like you took this derivative and multiplied both sides by dr. Essentially, that is what happens. It's just that dV dr itself, the derivative, is not a quotient of two things, but we define dV to be dv dr times this independent variable dr. All right. So what happens? We want to know that the change in v is within plus or minus something of this v, a 4/3 pi. But that's saying that the absolute value of the change in v is between 0 and like 0.001 or something like that. So it's the absolute value of this that we're interested in. That's what we want to say is small. That's the plus or minus part. But we get, this is the absolute value of 4 pi r squared dr. But we're putting in that r is 1. We're doing this when r is 1 meter. So we get that this is 4 pi times 1 squared times dr, but the absolute value of the product is the product of the absolute value, so we can split off this. Okay, well, this is already positive, so this is 4 pi times the absolute value of dr. But dr, this approximation is good if we make dr close to 0. But it's called dr because you're supposed to think of it as delta r, where delta r is small. But our delta r was this, right? What we're saying is that delta r, this information right here, is exactly the information that delta r is less than or equal to 0.001. That's what we're told, that the change in the possible value of r has absolute value less than or equal to 0.001. Expressing it in terms of absolute value is the same as saying that delta r is between negative 0.001 and positive 0.001. So what do we get? We get this is less than or equal to 4 pi times 0.001. And that's our approximation of how inaccurate. So we get that approximately the volume is approximately this 4/3 pi cubic meters to within 4 pi times 0.001. You know, we could get out a calculator and do this, but this is about 12. So it's approximately 0.012. Okay, that's differential approximation. It's where you're more concerned with the changes in quantities, and this kind of error analysis using differential approximation is actually fairly common. And the thing that bothers students the most about this is using the absolute values the way we did. This is what we were given. We used absolute values here, and here we use that the absolute value of dr is less than 0.001 to get that the absolute value of dv is less than or equal to something, so that we get this bound on how bad the volume can be. Okay. There's one other, aside from linear approximation, this function's approximately this, equal to this linear function, and differential approximation, there's one other approximation technique that relies on the same linear approximation, but it's in a different form too. And this is called Newton's method for approximating roots of functions, so places where functions equal 0. This really was Newton's method for approximating. And it will be easiest for me to talk about by going through an example. In the book, there's a list of steps, like you would, almost like a flow chart, or like you would program a computer. But Newton's method for approximating roots. And it relies completely on linearization. So what do? You start with some function. So actually what I'm going to do is the problem is related to the example we did earlier where we approximated square root of 0.99 by linear approximation. Let's approximate what? The square root of 99, of 0.99. Okay, but this time using Newton's method. So using Newton's method, what does this mean? So first, Newton's method is a method for finding roots of functions. So we need to write this thing we're after as the root of a function. Well, that's not difficult. So let f of x equal x squared minus 0.99. So that the roots of this function are exactly where this equals 0, so that f of x equals 0 if and only if x equals plus or minus the square root of 0.99. And we'd like to find one of those roots. Actually, either one, or approximate, either one would be fine. If it comes out negative, we could negate it to get something close to the positive square root of 99. How does Newton's method go? In your first step, you actually make a guess. Sometimes you have a good way of making a guess. Sometimes you really just have to almost pick a random value of x. We're trying to guess a root. Now, one way you could do it, if you don't want to be completely random, but there's no good choice, is one thing you could do, if you start with a continuous function, you can try to find some x value where the function's positive and some other x value where the function's negative. And then, if the function's continuous, then if it's positive one place and negative someplace else, it had to pass through 0 in between. So there has to be a root in between those two x values, the ones where you found one place that f was positive and one where f was negative. So you could, for instance, take the midpoint, add those two x coordinates and divide by 2. That's one thing you could do. In this problem, there's an easy first guess. We're trying to find the square root of something that's clearly close to 1. So we'll pick an initial x that is 1. But in other problems, it might not be so easy. So step 1, pick or make, guess, guess a root. So we'll call it x sub 0. We're actually going to have an iterative method. So we're going to start with an x sub 0 and produce something called x sub 1. And then we're going to take x sub 1 and use that to produce something called x sub 2. And we'll keep going until our approximation is good enough. Well, just because I'm doing it on the board and it's time consuming, good enough is going to be, we'll do 2 steps of Newton's method, but you can go on. And you can have calculators or computers do this. In fact, calculators, some of them of them have multiple methods for trying to find roots. And one is called a bisection method, and there's Newton's method, and then you can combine the two. But your calculator probably has Newton's method built in. So guess a root. We're going to guess x naught equals 1. And then what should you do? Well, really, you should go step 2. You should look at f of x naught. So calculate f of x naught. If that's really a root, then you're finished. Nice guess. You might as well stop. F of 1 for us is 1 squared. Right? Our function f of x is x squared minus 0.99. So so f at 1 is 1 squared minus 0.99. So that is 0.01. Well, it's not 0. So if that were close enough to 0 for us, for whatever purpose we had, then we could stop at this guess, but that's kind of boring to guess 1, so we're not going to stop. In the next step, you also need to calculate f prime at 1. All right, f prime of x is 2x. F prime of 1 then is 2 times 1, so it's 2. If this had come out to be 0, Newton's method would have a problem. We'll see why in a minute. And you would need to go back and pick a different x naught. If this had been equal to 0, you need to pick a different x sub 0. But assuming f prime is not 0, which it isn't in our case, then what do? You hope that you're near a root. And so step 4, approximate, and here's the linear approximation, approximate f of x by the linearization of f at x naught, and find where this is 0 instead of where this is 0. You're trying to find where this is 0, but we think this is close to this. So instead we find, this is approximately this. So instead we find where this is 0, and we'll call that x sub 1, and then we'll check. So, and find where, so what do? You find the linear approximation. So what's the linear approximation of f at x naught? It is, by definition, f of x naught plus f prime of x naught times x minus x naught. And we're going to set that equal to 0. And look where this is 0 and solve for x and hope that that's a root. It's definitely a root of this. We believe this is approximately this, or we hope that's approximately this, so that a root of this should be an approximation to a root of this. So we set this equal to 0 and solve. You would subtract f of x naught from both sides, divide by f prime of x naught, and add x naught. And what we get is that the next x value is our original x naught minus f of x naught over f prime of x naught. So this is what we get for the approximation of a root. And this is our next x value. Right? We picked an x naught, and we find that, oh, well, assuming this is relatively close to that, then a root should be very close to this. So we'll call this x sub 1. So we start with x naught, we generate an x sub 1. And in fact, every time we have an x sub n, next we'd have an x sub 2 with x sub 1 there, x sub 1 there, and x sub 1 there. So what are we getting for x sub 1? Oh, and this is why f prime of x naught needed to not be 0. If f prime of x naught had equaled 0, we'd have a problem right here. And we wouldn't be able to solve for the next x, and that's why Newton's method fails in that case. But in our case, what do we get for this approximation? We get x naught that's 1, then minus f of x naught. We already calculated that. That's f at 1, so that was 0.01. Divided by f prime at x naught, that was 2. So we're getting that this is 1 minus 0.005. Okay, that's 0.995. Oh, if you recall, that is what we got for our linear approximation of the square root of 0.99. We got 0.995 from the linear approximation. But the value of Newton's method is that we can just iterate this without any, it is just doing linear approximation again, in a sense, but it's, or not in a sense exactly, but it's, you can iterate it nicely. So what do? Well, now we don't go back to step 1, but now you come back to step 2, but you do this with, you calculate f of x sub 1. And if it equals 0, great, you're finished, you found a root. Or if it's close enough to 0 for whatever purpose you have in mind, then stop at x1. We're going to do one more step, except I won't calculate the numbers, and then you'd calculate f prime at x1, and you make sure that it's not 0. Need this to be unequal to 0. F of x1 is not 0. What is this? This is f of x1 is the 0.995 squared minus 0.99. This is not 0. And if it's not close enough for our purposes, then yeah, then you calculate f prime at x1. F prime is just 2 times x, so f prime of x1 2 times our 0.995. And then what do? You come back. You don't have to redo the solving this. Newton's method is always that the next x in your sequence of approximations, you take your previous x value, x sub n, you subtract f of x sub n divided by f prime of x sub n. And so, what would we get for x sub 2? So that means n is 1, so you get x sub 2 equals x sub 1 minus f of x sub 1 over f prime of x sub 1. So what do you get? You get x sub 2 equals x sub 1 minus f of x sub 1 over f prime at x sub 1. And this is x sub 1 was 0.995 minus f at x sub 1, which is 0.995 squared minus 0.99, all divided by f prime at x1, which is 2 times 0.995. Now actually you could switch into fractions and write this out as a fraction. If you want to do this by hand, it is done in the book. I'm not going to bore you with that. What you get is 79,000. You really can't do this by hand. Over 79,600. So that's what you get if you convert those into fractions, and then you can, if you want, you can calculate the absolute value of f of x sub 2. So, right, we want to know how close is this to being a root to our function. So you plug this back in the function, and close, we mean within plus or minus, so it's the absolute value of this, and you can check that if you square that and subtract 0.99, the difference will be less than 1 billionth. So it's pretty good. I'll say it again. How valuable is linear approximation, differential approximation, and Newton's method? Well, all of them are important. Linear approximation really does get used in a lot of physics and engineering applications where you want to get an approximate, you want to simplify some formulas if x is approximately something. And so you approximate it with the linear approximation. In the differential approximation, there's a lot of error analysis that goes on in measurements, and it's used a lot there. Newton's method, is probably the least used by hand. Yes, it's important to know it because somebody has to program calculators and computers to approximate roots of things that we can't solve for explicitly. So somebody has to know it. Can you get by with just your calculator? Probably, unless you're tested on Newton's method, and then you need to know it. But it is kind of cool just in, in theory, and also you can calculate by hand, and instead of getting decimals, you can get these cool fractions, of course. Cool is in the eye of or the mind of the thinker, so if you don't think that's cool, well, then yeah, then you should know it if you're going to be tested on it, and otherwise be happy knowing that somebody had to program that into a calculator or a computer.